Questions 42 to 52, the science passage on the reading of College Board's Test 4. So, last passage on this test, this very difficult reading test, mind you, is the science passage. The passage is adapted from Carolyn Gramling, Source of Mysterious Medieval Eruption Identified. So this title is great, just like all titles on all science passages. They tell you pretty much what we're about to read. And in this case, the title of this science passage tells us the source of mysterious medieval eruption identified. We identified a mysterious medieval eruption. Okay, so we're going to find out probably something that has to do with geology and the medieval eruption of some volcano or something. You don't need to know anything about science in order to do well on these. I can't stress that enough. I can't stress it enough. I don't care if you're the worst science student in the whole universe. That's not an excuse to get questions wrong on the science passages of the test. You do not need to know anything about science in order to do well on this section. I think that the science passages are the easiest passages on this entire test because they just tell you everything you need to know. If you remember what the author told you, if you remember the development of the experiment, of the study, of the field, you'll be fine. So a thorough understanding of the text for me is very important. Let's understand what this piece is about. Let's analyze the passage. Let's talk about the things that matter before we dive right into the questions. About 750 years ago, a powerful volcano erupted somewhere on Earth, kicking off a centuries-long cold snap known as the Little Ice Age. So something erupted 750 years ago, and that cooled the Earth for several centuries. Identifying the volcano responsible has been tricky, and we're probably going to find out based on this title, but now we found it. That a powerful volcano erupted somewhere in the world, sometime in the Middle Ages, is written in polar ice cores in the form of layers of sulfate deposits and tiny shards of volcanic glass. So we're able to use core samples from the polar ice in order to see layers of sulfate deposits and tiny shards of volcanic glass to see, oh, an eruption occurred at this time. It's almost like you dig the core of the Earth and you see the different layers that have deposited on the surface over the last hundreds of years. These cores suggest that the amount of sulfur the mystery volcano sent into the stratosphere put it firmly among the ranks of the strongest climate-perturbing eruptions of the current geopolitical epoch, the Holocene, a period that stretches from 10,000 years ago to the present. So this is the strongest climate-disturbing, climate-affecting eruption in our current geological time, which is this 10,000-year band of time, from 10,000 years ago to the present. A haze of stratospheric sulfur cools the climate by reflecting solar energy back into space. So it's almost like a reverse greenhouse gas. It blocks the Earth from accepting sun's rays into the atmosphere. So as a result, a lot of the sun gets bounced off and the Earth cools. And it creates a reinforcing cycle that cools it further and further. In 2012, a team of scientists led by geochemist Gifford Miller strengthened the link between the mysterious eruption and the onset of the Little Ice Age. So we strengthened the link. We found out how the eruption was related to the onset of the Little Ice Age. By how? Using radiocarbon dating of dead plant material from beneath the ice caps of Baffin Island and Iceland, as well as ice and sediment core data, to determine that the cold summers and ice growth began abruptly between 1275 and 1300 CE and became intensified between 1430 and 1455. So AD, understanding the Common Era. So what happened? This guy in 2012 found a link between the eruption, this mysterious eruption, and the Ice Age by using radiocarbon dating. So he used radiocarbon dating to date that the cold summers and ice growth began abruptly 1275 to 1300, and the year 1275-1300, and it got really bad 1430 to 1455. Such a sudden onset, remember, because they said it was began abruptly. Such sudden onset pointed to a huge volcanic eruption injecting sulfur into the stratosphere and starting the cooling. So sulfur was ejected from the volcano, which masked and clouded the whole Earth with a dark reflective shield that prevented sun from getting in. Subsequent, unusually large and frequent eruptions of other volcanoes, as well as sea ice ocean feedbacks, persisting long after the aerosols have been removed from the atmosphere, may have prolonged the cooling through the 1700s. So this event that happened in 1275 through 1300, its effects were still felt all the way into the 1700s. Volcanologist Frank Levine and colleagues now think they've identified the volcano in question, Indonesia's Samalas. So they found this guy, volcanologist, Frank Levine. They think they've identified it. They found out. So this guy, Miller, determined there was a relationship between sulfur and its effect on the Little Ice Age, and they found that this sulfur deposit corresponds to 1275 to 1300. And this guy, Frank Levine, identifies the Indonesia's Samalas volcano as probably being the cause. One line of evidence, they note, is historical records. According to Babed Lombok, records of the island written on palm leaves in Old Javanese, Samalas erupted catastrophically before the end of the 13th century. So they have written record. They have a record that was written on palm leaves that this volcano erupted before the end of the 13th century. It makes sense. It erupted 1275 to 1300, which is what Miller says when the cooling started abruptly. Devastating surrounding villages, including Lombok's capital at the time, Pamatan, with ash and fast-moving sweeps of hot rock and gas called pyroclastic flows. So this seems to be lining up. The written history of the island seems to be lining up with the core samples that were radiocarbon dated by Miller. The researchers then began to reconstruct the formation of the large 800-meter deep caldera, a basin-shaped volcanic crater. So they're defining what the caldera is. They reconstructed the formation of this caldera that now sits atop the volcano. They examined 130 outcrops on the flanks of the volcano, exposing sequences of pumice, ash hardened into rock, and other pyroclastic material. So they were able to examine the outcrops surrounding the volcano, the volume of ash deposited, and the estimated height of the eruption plume, 43 kilometers above sea level, put the eruption's magnitude at a minimum of 7 on the volcanic explosivity index, which has a scale of 1 to 8, so that's pretty strong. That's on the upper end of the this is the end of the world volcano level, making it one of the largest known in the Holocene. So this is in this era. This is the largest volcanic eruption in our modern period of geologic history. The team also performed radiocarbon analyses, so this is very similar to what Grifford Miller did, on carbonized tree trunks and branches buried within the pyroclastic deposits. So they were able to measure, I guess, the date of the trees that were and branches surrounding it that were, leveled by the magma and the ash, to confirm the date of the eruption. It could not, they concluded, have happened before 1257, and certainly happened in the 13th century. So this is all in line. We have Grifford Miller's analysis that this happened probably in the 1300s. We have written records that say that it happened right before the 13th century, so the end of the 13th century, which is the end of the 1200s. And we have radiocarbon dating from the trees surrounding the eruption of this island, of this volcano, Samalas, which puts it in the 13th century and no earlier than 1257 AD. It's not a total surprise that an Indonesian volcano might be the source of the eruption, Miller says. So now we're kind of talking about these passages follow a very linear manner. They talk about some issue or some unknown thing, then they talk about how they found something, and then at the end there's always the scientists opining and discussing the implications of their findings, whether it's good or bad, or I agree or disagree. It's not a total surprise that an Indonesian volcano might be the source of the eruption. An equatorial eruption is more consistent with the apparent climate impacts, and, he adds, with sulfate appearing in both polar ice caps, Arctic and Antarctic, there is a strong consensus that this also supports an equatorial source. So Miller, the guy who did the geochemist who led the first team of radiocarbon dating of when the ice first started to occur, he's saying that he thinks there was an equatorial eruption. It happened on the equator, on the that middle band of Earth, because he thinks that's true because of the way that it affected the climate, and also because of the location of sulfur that was found. or sulfate that was found rather, both on the north and south pole. So if that means that it probably was in the middle, because if it was equally distributed in the north and south, it was probably sourced from the middle. Another possible candidate, so now we're throwing a wrench into our working theory. Another possible candidate, both in terms of timing and geographic location, is Ecuador's Quilotoa, estimated to have last erupted between 1147 and 1320. So this is another theory they have, like another volcano. We're not 100% sure it was from Samalas. We think it might be from Quilotoa, potentially, maybe. But, so now here's like a reversal. But, so we think maybe it's from this other place, from Ecuador. But when Levine's team examined shards of volcanic glass from the volcano, from this volcano, remember this guy is the volcanologist who did work in Indonesia, Samalas volcano. When this guy and his team examined shards of volcanic glass from this volcano, they found that they didn't match the chemical composition of the glass found in the polar ice cores. Whereas Samalas glass is a much closer match. That, they suggest, further strengthens the case that Samalas was responsible for the medieval year without summer in 1258 CE. They offer at the end an alternative hypothesis, an alternative volcano of where they found it and what happened. They found that the glass from the volcanic glass and shards from Quilotoa, from Ecuador, did not match the glass that was found in the polar cores. The glass from Samalas was a much closer match. They think that Samalas was responsible for this ice age. Very straightforward passage. Let's just not mix stuff up. Let's not mix the locations up. Let's not mix up what they said. Let's not make stuff up. Let's make sure that our timeline of chronological events is consistent, and we will be fine. So let's take a look at the questions.